First, I'd like to thank the organizers for putting this workshop together. It's been a really interesting one so far, particularly the most recent talks, which both set up this talk, and in some ways, I think that Bill almost could have given this presentation for me. Also, of course, I'd like to thank my collaborators and Laser Program for funding, and also a special note to Raul Baragiola, who was gracious enough to join one of our teleconferences, and I think that the dialogue that we had helped to promote understanding between our groups and about the solar wind implantation process in particular. And so as a result, I've sort of changed my title, and we're going to, in this talk, I'm going to tell you about our laboratory studies on proton and deuteron implantation into lunar soils. Of course, the impetus for this study is the observation, as we've heard many times now, of the OH signals observed by BIMS, epoxy, and M-cubed, and what is the origin of this signal and the compositional dependence and potential diurnal variation. I think Ray Gibson gave a very nice talk just now showing how much hydrogen there is in lunar soils. And so this follows nicely, this study follows, I think, well on his talk. So, of course, this is a space weathering is the main process, and sort of pointing out that it's the solar wind that we're talking about. This is mostly focusing on mid-IR studies. So the idea is that solar wind implants protons that combine with oxygen and silicates to form OH. And there's been many studies on this, particularly early ones, putting forth this idea. And some of the ones that included mid-IR studies include these by Zeller, Mattern, and other people, where they saw a definitive hydroxyl signal. So what I'm going to tell you about now is sort of our published work and this sort of continuation of that, which we used a mature highland and submature Mare soil and implanted it with low energy 1 keV proton and deuterons. So our laboratory studies, we are somewhat limited in equipment, nevertheless doing the best we can with things that are available. And I think that the previous talk showed that the hydrogen comes off quite readily at about 500 degrees C. And so to prepare the lunar soils for our IR studies, we heated them under vacuum for 2 hours at 500 C to drive off the, of course, adsorbed water and intrinsic OH. These were air equilibrated samples that we had used. Our proton and hydrogen and deuterium ion beam characteristics are here, 2.2 keV. And the idea is that in our ion gun, in this Gatan ion beam system, the most likely source of the protons and deuterons are hydrogen molecular ion and deuterium molecular ion, giving us about 1 keV per particle. Now, one of the limitations of this is that we do not have ultra-high vacuum, and so we just come out and say that. And the samples have to be transferred in air. And so this, of course, necessitated the deuterium experiments, which then, because of the low natural abundance of deuterium, allows us to pinpoint the source of the signal, as well as control experiments to understand the effects of holding samples, deuteron implanted samples, at ambient conditions for days and indeed up to over a month, to prove to ourselves and the community that the signals we're seeing were not due to ambient water. So in a nutshell, this next slide summarizes our results that were published last year. And on the left-hand side, we're looking at a series of spectra from a highland sample, and on the right-hand side, the Mare sample. The black trace in each is the air equilibrated IR spectrum, and the blue and red traces are the hydroxyl and deuteroxyl spectra after proton and deuteron implantation, respectively. So, the main features of this are that the deuteroxyl signal is at the expected, isotopic shift, and so that we are creating essentially the same species that is formed from the proton implantation in both the highland and in the Mary samples. And the signals that we observe are consistent with the epoxy VIMS and M-cubed data, even though those didn't go out, of course, as far into the mid-IR. Now, the process that this goes by, and I think, Bill pointed this out, and as others speakers, that, the lunar soil is very heterogeneous. And so here is a TEM image by Wentworth, and showing the surface of the lunar grain, and it's an amorphous glassy rim that has nanophase iron embedded in it. The proton and deuteron ranges, or sort of maximal range, is given by the sort of the yellow and green bars respectively, so up to about 50 nanometers in depth. So the range, depends on, of course, the energy of the particles and the density of the target. And this is just a simple simulation using the SRIM software by Ziegler with a limited number of trajectories so that it's easier to see. And on the left-hand side, of course, of this image is the surface, and it goes to a depth of about, this is in angstroms, 500 angstroms or 50 nanometers. And what you immediately notice is that the trajectories in the lunar soil are very complex. Each proton, as it embeds, loses kinetic energy until it either finally comes to rest, is implanted, captured. Trajectories that meet the surface again imply backscattered protons. Things that are not shown in this image are the sputtering of light elements, such as oxygen. And there's all of these trajectories, this radiation damage, results due to the loss of kinetic energy. And so the specific, chemical species, the nature of this surface, I don't think we understand it very well, at least I don't. And the effect on that has on forming water, OH, and water. And so what is the chemical nature? Is it more porous? Well, most likely. Is it more reactive? Probably. Is it reduced? Yes, it probably is reduced as well. We'll talk about that in a minute. And another process that Bill mentioned is in addition to sputtering, is one that's a sort of chemical exchange. And so in this experiment, also from the same publication, we used the Stillwater plagioclase specimen that was heated to try to attempt to drive off all of the OH and water. We only partly succeeded, and so that when we did the deuteron implantation, we saw a nice deuteroxyl band, but also the sharp band at corresponding to the frequency shift of the OH band at 3 microns. So the mechanism that depletes the OH is certainly going to be sputtering. Certainly there's a possibility of chemical exchange of deuterons for protons. Things that we did not test in this, but following the chat, this just makes it sort of distracting in a meeting, following a chat, listening to a talk, thinking about one's own talk, about the importance of ultraviolet light, photon bombardment of cleaving OH, light and heat. Of course, there's a large diurnal temperature variation. And the spectrum that are shown here, that is the loss of OH by deuteron implantation, is also observed in IR spectra for the highland and Murray soils. Okay, so this seems all well and good, but there, is a conflicting report, and I think, and this is a publication by Burke et al. And from Baragiola's group, and we're looking at XPS spectra of anthracite and ilmenite slabs that were irradiated with a proton beam. And one of the interesting things about this very fine paper is that the IR spectra did not show evidence for hydroxyl production, but rather hydroxyl loss, and that's consistent with their SIMS data. But let's focus a little bit on the OH XPS, or the oxygen XPS spectra. And what you can observe is that this is before radiation on the left and after radiation on the right, that there's a loss of oxygen in the outermost layers of their specimen. And this is...
Hey, Andrew, you have about 90 seconds left.
Thanks, Mark. Okay, thank you. And so this is consistent with Keller and McKay's TEM images, and so there's clearly a surface reduction going on. So this also, after our discussion and examining this data, suggests that we should do some additional experiments, and so to help control our own, previously to build on our own published work. And what we do in this study is to maintain the specimen under a reducing environment. And so in the bottom trace here, this is the air equilibrated spectrum of a highland soil, Apollo 16, so it's showing distinct OH. B is a baked out sample, so there's neither an OH or OD. C is just a deuteron implanted. And in spectrum D, we have a deuteroxyl signal. And after exposing it to hydrogen at an order of magnitude higher pressure for a relatively short time, about an hour, we still did not see a hydroxyl signal creeping in. And so, but in any case, at least we did not expose it to air between measurements, and maintained it under a reducing environment at least. In our next experiment, then, we exposed the sample after deuteron implantation to a much longer time to a hydrogen environment. So the spectra A and B show the deuteroxyl signals that are the same as the last two in the previous slide. And so focusing on spectrum C, we have both a deuteroxyl band as well as a hydroxyl band that's crept in after 14 hours of exposure to a 10 to the minus 4 torr environment of hydrogen under a dynamic vacuum. As a control experiment, we put the baked out sample of the Apollo 16 soil into the same apparatus and exposed it to a hydrogen environment without deuteron implantation. And again, we see a hydroxyl signal forming. So this is interesting because it sort of goes back to Chad Room and Bill's talk, where he mentioned diffusion as a possible role in creating water. Certainly, we can do the reverse, at least, and take a hydrogen molecule and form OH in this lunar sample. So in these experiments, our outer surface is depleted of oxygen because it was exposed to the ion beam. But we nevertheless feel that these experiments support our previous work, that the deuterium implantation or the deuteroxyl signal is due to deuterium implantation rather than diffusion of deuterium in, because of the much longer time scale, the long time it took for hydrogen to come in and form a hydroxyl signal. So, to sort of come to a close here, this suggests other types of experiments and potentially raises other questions. In conclusion, I think our data shows that the solar wind is the likely source of the hydroxyl signal. And yet, in our own experiments, do we have a bias from, say, deuterium molecular ion or hydrogen molecular ion beams? Other things we'll test are highland versus Mare soils and raise the question of exploring the idea of diffusion and UV illumination on hydroxyl formation. And to me, one of the things that comes out of this work, and Bill attempted to answer some of this, is that if we have solar wind is responsible for the OH, and yet the outer surface of the soil is reduced by sputtering loss of oxygen, and how is water forming? there are many processes that can take place that have been mentioned in diffusion, radiolysis, this kind of thing. And again, I think one of the persistent questions is what is the sort of the atomic or the molecular chemical nature of this radiation damage that results in the OH formation and potential water formation. And I think the last comment is also been mentioned before, diurnal insulation. And thank you very much for your attention.
Okay, just before I start the questions, I want to remind again the next speaker to get ready. And the question we have from Indu is, how does porosity affect implant-associated reactions?